Hi everyone, we are Group 36, aka Pegasus Protection Services, and for our critical design review, we are going to talk about our security system. Now, one of the big motivations for us designing the system the way that we did was we wanted to find a project that included not only hardware components, but a significant software component as well. And being that we're all computer engineers, we felt comfortable handling that large software component, which we will talk about a little bit later. Essentially, what we wanted to do was create a security system that could be used to monitor personnel entering and leaving secure locations. And you can think of a location such as a secure server farm, where you want to be aware of who is entering that server farm, where they are when they're in the room, and how long they're there for. And with this security system, we will be able to do that. And as I mentioned before, we have a few large components to this project. The first is the visual tracking component, in which we have facial detection, facial recognition, as well as a backend connection to the website, which will send live updates of any tracking that we have there. And the next component is the real-time location tracking, and we'll be using a trilateration algorithm to get the accurate positions of any tagged users in the location. And that will also provide live updates to the web app, and on the web app you will be able to see that in-field beacons will be made visible on our map, and that will sort of show where the user is at any given moment. And finally, we have our web app, and we want it to be intuitively designed, as well as we want to include encrypted data transfer between the web app and all the rest of the components. And on this web app is where we're going to do most of the handling of the system data, such as entering new users into the database, viewing the live camera feed, and also viewing, of course, the location tracking. Here we have the system overview diagram, and on the left we have a Bluetooth Low Energy or BLE tag that will ideally be held by the individual entering the secure location. This tag will communicate using Bluetooth to several beacons throughout the location, and each beacon will use Wi-Fi to then send that location data to our Jetson Nano, where the information will be processed and sent to the web app. You might also see the camera module there, which is connected by SPI to the Jetson Nano. This will provide our live camera feed to the web app and will be where we make use of that facial detection algorithm as well. And here we have our system behavior, and I will discuss the expected behavior of our security system in a few situations it may encounter. To begin, the first one is where a non-employee enters the location, and this just means that the facial detection software fails to recognize this person's face, and there's also no tag detected entering. And what will happen here is that it will send a warning to the security software and will also screenshot the user's face for further processing. The next situation is where an employee with unauthorized access tries to enter. An alert message will be sent again, and a note will be added to that employee's database. Otherwise, the tracking and the facial recognition will execute normally. And in the next situation, the ideal situation, there's an employee who enters and they're authorized. All we'll do is link up the beacon to the name, and we'll just have normal operations there. And multiple employees enter. In this case, we just have to be aware that the camera system itself should be aware of the relative position of the two users and be able to identify who is who, but really normal operations in that case as well. And in the case that a tag is identified but there is no face to match, we will let it run for about a few seconds just to make sure that the facial recognition gets a good chance at detecting them, and if it doesn't happen, then we will just take a screenshot and send an alert to the system again. And here I'll talk about our requirements and specifications. And we want the system to be able to detect the tags within a 1 foot accuracy, just to make the live tracking clear. And the facial recognition system should have a range of about 5 to 10 meters away from the entry location. And the size of the beacon should be no larger than about 120 by 70 millimeters, should be able to fit in a pocket. And another specification is that we want the BLE signal frequency to be around negative 67 decibels, so that it doesn't interfere with any other signals such as Wi-Fi. And all of the components should communicate wirelessly with each other through either Bluetooth or Wi-Fi, as mentioned before. And we want the positioning to update within 1 millisecond to keep it relatively quick, and the beacon should be able to detect tags within 10 meters. Now, as for some design constraints, part shortages were had a big effect on how we designed this project. For example, we could not find this voltage regulator, the LMR 504, so that drove us to use the LM7805, which is a very old and pretty inefficient voltage regulator, and that's what we used on our first generation PCB design there. And tag size and portability, as mentioned before, we want it to be small enough where you can just sort of put it in your pocket and get it out of the way. And we are not sponsored. This is also funded, so we wanted to try and keep the cost as low as possible. And the Jetson Nano versus Raspberry Pi, that sort of plays into part shortages there, being that the Raspberry Pi wasn't in stock, but also the Jetson Nano is generally more preferred for facial recognition, facial detection type of projects. And here we have the Jetson Nano specifications, and we decided to pick this just because it was popular for computer vision projects, and it supports 4K 60 FPS video, which is great for us because we want the best quality we can, and this will support our project's facial recognition software as well, mainly. And here's the Raspberry Camera 2, and this has an 8 megapixel resolution, and it's able to run 1080p at 30 FPS, which is good enough for us. It allows for the proper distance that we were looking for, as well as it was affordable. So this is really the perfect camera for us.
With face detection and recognition being a key piece to how we interpret the images being streamed from our cameras, we allocated some time towards finding tools that can aid us in achieving these two features. While there are plenty of online resources commenting on various ways to do this, our group has opted to utilize OpenCV and Python as the core to work towards implementing face detection and facial recognition. For those of you not familiar with OpenCV, think of it as a collection of methods that you yourself can call on to help achieve a variety of topics in the computer vision field. We thought that these libraries would fit best with our desire to code in the Python language, and thankfully, OpenCV is supported on Python. To list a few of the packages we are particularly focused on for this project, it would be the object detection and face analysis modules from OpenCV and a facial recognition package in Python. The first task that our computer will need to perform while receiving the stream of images from our cameras is known as face detection. In layman's terms, face detection aims to locate faces in an image. One way a computer can do this is by looking for features of a face, maybe an eye, mouth, or nose, for example. Another way could involve the computer looking for facial structures or patterns in the image. In the end, the computer will classify the image it is looking at as one that contains a face or one that does not contain a face. For our case, we will primarily be using the HAR cascade classifier provided by the OpenCV to allow our computer to perform face detection. With some group members having prior experience to the HAR approach and an acknowledgement of how computationally expensive the other methods are, it makes sense to use it. Now that our computer is capable of detecting faces, it can now serve as the prompt to the following task that our computer needs to perform: facial recognition. As the name suggests, facial recognition is a task that seeks to identify the face that is being perceived by the computer. In order to recognize a face, the computer must have references of that face prior to allow it to make the connection. Once it has the references, the computer will begin to compare the incoming images to ones it already has, and if similarities are present, it may be able to map the face to a name. That being said, there are some things that need to be taken into account. Firstly, we are positioning the cameras to be able to capture frontal face images, and if an image captures a person at a different angle, it may be less successful at making the connection. Face accessories also create problems for this technology, as similarities perceived for someone with a mask may not be enough for the computer to come to a conclusion. The main necessity for both face detection and facial recognition are images that can be used to train the computer so that it can comprehend the incoming images from the cameras. Fortunately, face detection is a concept that has been explored many times, and as such, there are plenty of online datasets that provide images we can use to train each method. For face detection in particular, there also need to be non-examples, or images that do not contain a face, so the computer is able to make that distinction as well. As for facial recognition, it too will need faces, but more particularly speaking, it will need a collection of images for each face that is supposed to be recognized by the system. As mentioned in the slide before, we are storing 10 or more images per person to allow sufficient information for the computer to reference from. Here is a brief illustration of how the computer vision will work in our system. From the camera, images will be passed to the Jetson Nano, from which then the Nano will be responsible for spotting faces in those images. If the Nano were to spot a face, that image would then move to the identification phase, where the Nano will try to put a name to the face it is perceiving. If, in the unfortunate circumstance, the camera is not able to identify a face in the image, like this cat over here, perhaps there is an intruder, an imposter, if you will, that has infiltrated the system, and therefore an alert will be raised, signaling for an emergency meeting to be scheduled that will investigate the footage and see what triggered the camera. Now we will discuss the successes and troubles we've encountered while working to implement computer vision into our system. At the current moment, we have installed both Python and the OpenCV libraries onto the Jetson Nano. We took some time to modify our Nano to incorporate a small fan as we found while using it that the heatsink would become fairly warm. The Nano is now ready to execute programs involving face detection and recognition, and our group is in the process of setting that up. The good news is that there are a lot of resources online denoting various manners for implementing both technologies. On top of that, once we get each technology configured, the code for linking the two programs should be straightforward. On the other hand, we have run into some obstacles, such as how using multiple models would affect the latency of the result, or trying to better judge faces that may have masks on them. Additionally, the Nano's memory is something that could limit the overall speed of this entire process, as our Nano only comes with 2 GB of RAM and may have to segment larger computations if it does not have enough space. That being said, we will work around the Nano to implement a system that best suits the Nano's capabilities.
For our microcontroller selection, we went with the ESP32. Some of the benefits here was that the power consumption was low. And then it also supports Bluetooth, specifically BLE. So Bluetooth Low Energy was a big factor, and ESP32 is generally used across many Internet of Things projects. So that was, ESP32 is definitely a perfect selection here. For our communication method selection, we went with BLE, like described in the previous slide. With that, we'll be able to use our indoor positioning system, and it'll be more accurate with BLE compared to other methodologies based off of the latency, its range, and its power consumption. In our trilateration implementation, there's a few hardware requirements. One being there needs to be at least 3 beacons present in the room, as well as 1 tag for the system to work. There's going to be software requirements as well. We'll be using Arduino to program the microcontroller, web app to display it, and a database to store the information that goes behind it. So in the implementation of trilateration, there's some things that happen with the signals and their paths. So we'll be using a distance estimation formula to calibrate the distance in the real world to the measured signal that the Bluetooth is receiving. So that distance is the first thing that needs to be estimated. Once those numbers are found for each of the 3 beacons, then there will be a point estimation formula ran on that, and that will actually get um, our coordinates closer to the real indoor position that we want to see in our dashboard. So for data transmission, obviously these signals need to speak to each other and also send important data. So for our microcontroller and our BLE tags, they will be sending unique identifiers back and forth to each other. Now the microcontroller is going to take that information and send that to the Jetson Nano. And so on the back end, the Nano is going to already, or is supposed to already have some information in the database that lines up with those unique identifiers, as well as a timestamp for our security system. So some previous considerations, RFID, which didn't have enough in terms of what we needed for the indoor tracking. Wi-Fi, we were going to use cell phones as tags, which is still a consideration, but we wanted to make something, so our PCB kind of replaced that, and the Bluetooth tag did as well. And then ultra wideband was also considered. So in our first gen PCB design, the goal there was to get something that worked essentially with a voltage regulator and something that would be consistent, and that was also small enough to fit in small spaces. So some of the results from our initial testing, we were able to get the voltage regulator to do its job and do a voltage drop down to 5 volts. And so that's displayed in the picture there. There were some failures along the way, those being a capacitor almost blowing up in the lab. But at the end of the day, we were still able to get the PCB working through testing, and we were able to order it. And so this is what the PCB currently looks like. And then the BLE tag will be arriving soon. We don't have it yet, but this is about how small it's going to be.
Due to the simplicity and board size of our first gen PCB, we decided to construct a second gen PCB. This second gen PCB will still use the ESP32 chip module for its Bluetooth and Wi-Fi features. For the second gen PCB, we essentially created our own dev kit for our module. Our PCB design consists of 3 main systems. On the left, you will see our voltage regulator system. Our PCB can be powered on either by a micro USB or a LiPo battery. We decided to add the LiPo battery component so that our beacons can become more portable. Our regulator takes in 6 volts micro USB and 4.2 volts from the LiPo battery, which then outputs a 3.3 volt to our ESP32 module, which powers on the chip and essentially our PCB. We then added a LiPo battery charger, as you can see in the middle. The MCP73831 is designed to charge a single cell, and we added an LED indicator to the stat input to display the status of the charge. Ultimately, the most important part was getting our USB to serial converter set up. This will make our life a lot easier when we are pushing our code onto the ESP32 module. Here you will see our new PCB board design. As you can see on the board, we added 2 buttons, which is used to reset and boot the ESP32 module. These were recommended to implement by the ESP32 datasheet. This board is a lot smaller than our first gen design. It is 2.1 inches by 1.3 inches and uses surface mount components, which overall made our design much smaller. This is our current housing design for our PCB. We plan on really just placing the PCB board inside. Overall, this design is not yet finalized. We still need to add a couple holes in order to connect our battery and USB to the board, as well as a section to place the battery in order to keep everything nice and secure. We are waiting on the arrival of our second gen PCB to come in before making these edits to our final chassis. Finally, at the heart of our project is our web app. The application is a major part of our project as it brings all of our systems together into one unit. The application allows users to interface with IoT so that they can view and send data. Our application will also be able to display recently captured activity on the admin dashboard. Admins who have access to our system will be able to assign BLE tags to specific users, as well as be able to upload images for our facial recognition system. The application will be using AWS IoT Core to send and acquire data via MQTT. The MQTT protocol is used to carry messages from these devices. So in our case, we want to carry information from our ESP32 beacons onto our web app in order to display real-time location. We also plan on having a real-time video stream of our camera module, and this will be done using Python's Flash framework. Ultimately, the front end of this web app will be done using React, and the back end will be done using Node.js/Express. Here you can see a skeleton of our front end design and how we plan on displaying the live camera feed and indoor tracking system. To the left, you can see the live camera feed, which a user can navigate to using the sidebar. In the middle, you will see our admin dashboard/homepage, which will essentially have information such as how many users are in your system, how many alerts have been signaled, as well as a table that displays latest tracking. For example, let's say we have a user named Christian Silva and he's assigned a random tag. If he has been near any beacon, the table will populate an entry that shows his tag ID, his name, and the location relative to the nearest beacon and the date that this entry took place. To the right, you can see how we plan on implementing our indoor tracking. Users will be responsible for uploading floor plans of their location. After that has been done, they will see 3 small target icons. These represent our beacons. The user must drag and drop these icons to where the beacons are placed in the building, respectively. Once that is done, our initial iteration technique will kick in and start displaying a user icon which shows the user's location in real time. This table shows our work distribution for our Senior Design 1 project. I, myself, Christian, am working on the web app, working on the PCB and the IoT connection. Dylan will be assisting me with the web app and the IoT, however, his primary focus is with our computer vision system. Andre also worked on the PCB design as well as the beacon firmware and is working on the indoor tracking software. Isaiah is also responsible for the beacon firmware and the indoor tracking software and plans on assisting Dylan and I when it comes to the IoT. Here you can see our project budget and financing. We made it our goal to not exceed $400. As of now, we are slightly over $250, and the only thing we have left to really buy is our housing for our chassis, which we do not think will exceed over $400, so we are well within our range. We believe to be making good progress. For research, we like to say we are 95% done, but in reality, there's always something to research and look into. For our part order, we are 80% done. We are still waiting on the arrival of our second-gen PCB design and the parts needed to create our chassis. Our PCB components of our project is about 75% done. As I stated before, we are waiting to solder and still test our second-gen PCB design. Our indoor tracking, computer vision, and web app are slightly below 40%, and our chassis is about halfway done. We just need to add a couple more parts here and there and add a top covering to it and add some 3D printer design, but overall, we are slightly halfway done with our project. Our immediate plans of success really involve 6 key steps. We have to solder and test our second-gen PCB design, complete our shell iteration implementation and our computer vision aspect of our project. We then have to successfully implement the MQTT protocol and the Flash framework to get that live indoor tracking and the live camera feed. And then once we put everything together, we have to test our final prototype. For testing, we have to make sure that each subsystem is working as expected and that our alert logic on our web app works correctly with our systems. At this time, we are open to any questions you may have.